Hello everyone. Today I am starting the lecture of algebraic structure, and these videos will be beneficial for all those students under GIS group IT 4th semester, okay, or IT second year. So in algebraic structure, basically this is the main topic of group theory. Okay, so in this video we will discuss about the binary composition and what is group theory and how to show that a set with an binary operation that will be a group. Okay, so let's start today's topic. First topic, that is binary composition. So first of all, we have to understand the definition of binary composition. Suppose we have a non-empty set capital A. Okay, we have a set obviously non-empty means A is not equals to 5. So we have set non-empty set capital A which is not equals to 5. Now the cross product, that means A cross A. Okay, so you have a set and this set is A cross A and the single set capital A. A mapping from the set A cross A to the set A, this mapping is called binary composition. Okay, this mapping is called binary composition, or it is also called binary operation. Binary operation. The word by is written because here the mapping is between the set A cross A and the set capital A, and the elements of the set capital A cross A, that will be in ordered pair form. Ordered pair means A comma B. Okay, ordered pair form, and obviously the order of the elements, this is very important. You cannot change the order of the elements. Okay, because ordered pair A comma B is not equals to ordered pair B comma A. In general, ordered pair A comma B is not equals to ordered pair B comma A. So order is very important. That's why this type of element is called ordered pair. Okay, now so what is binary composition? Binary composition basically a mapping which maps from the set A cross A to the set capital A. So what will be the definition? Let capital A be a non-empty set. Be a non-empty set. Okay, a binary composition or you can say binary operation. Binary operation on capital A is a mapping from, or you can denote mathematically, is a mapping F maps A cross A to the set A. Okay, and this mapping is called binary composition or binary operation. Clear? Now we denote this binary composition using the symbol circle. Okay, in some textbook they use the symbol star, or you can use addition in circle. Okay, or you can say multiplication in circle in this way. Okay, we can denote the binary composition using the symbol this circle. Clear? Now if the circle is commutative, then we can say that commutative binary composition. If it is associative, then we can say that associative binary composition. Okay, suppose we have a set G, and obviously this is not equals to 5. Okay, we have a set G and there is a binary operation circle. Now this system G comma circle, that means the non-empty set G along with the binary operation, this is a system. This system is called groupoid. Okay, this system is called groupoid. For example, suppose I am writing set of integer Z, and let's say the binary operation is addition. Binary operation, this is nothing but the operations. Okay, addition, subtraction, multiplication, matrix multiplication, matrix addition, etc. Okay, so binary operation. So we have a non-empty set Z, set of integer, and and a binary operation addition. So obviously this forms a system, and this system Z addition, this is a groupoid. Okay, similarly you can write, let's say R, set of real number, R addition, this is also a groupoid. Okay, or you can write Z dot, this is also a groupoid. Set of rational number Q addition, this is also a groupoid. Okay, in this way. Now if the binary composition which I am using, if the binary composition is commutative, then we can say that this is commutative groupoid. Okay, if the binary composition is associative, we can say that associative groupoid. Okay, now there is a very, very important concept which is identity element. Identity element. What is identity element? Suppose we have a non-empty set G, okay, and there is an operation, binary operation. Okay, so G is non-empty set and circle, this is binary operation. So obviously this system G comma circle, that will be called a groupoid. Okay, and all the elements in G, let's say I am taking any arbitrary element A, Now you have to find out an element from the set G such that if you apply the binary composition with the element E, okay, so A composition E, this is equals to E composition A, and that will give you the same element A. Okay, and for all A belongs to G, this result must satisfy for all the elements in G. Then the element E is called identity element. Okay, for example, suppose I am taking the set is Z addition. Now from the set Z, choose any arbitrary element. Suppose I am choosing plus 2. Okay, now you have to find out an element so that you can add the element with 2 and you will get the result 2. Is it possible? Obviously possible. There is an element 0. So 2 plus 0, or in another form 0 plus 2. In both direction you are getting the result 2. Similarly, take any other element 3. 3 plus 0, this is equals to 0 plus 3, this is equals to 3. That means in Z addition, addition is the binary composition, you are getting an element 0. If you add the element 0 with any element from the set Z, you will get the same element. Okay, that's why 0 is an identity element of Z addition. Clear? Similarly, you can find out, suppose I am giving you an example. Suppose Q, set of rational number Q dot. Set of rational number Q dot. Okay, now tell me, what is the identity element in Q dot? Choose any arbitrary element. Okay, suppose I am taking half. Okay, here the operation is multiplication. Dot means multiplication. Okay, Q dot. So you have to choose an element so that if you multiply the element with half, you will get the same element half. So obviously the element is 1. Half into 1 or 1 into half. In both cases you will get the result half. If you choose any arbitrary element, let's say 1 by 5. 1 by 5 into 1, 1 into 1 by 5, you will get the result 1 by 5. That means here 1 is the identity element in Q dot. Clear? So this is very, very important concept in group theory, identity element. Okay, suppose I am giving you another example, set of natural number. Okay, and the operation is, let's say, dot. set of natural number and the operation is dot. Can you tell me what is the identity element in this case? What is the identity element? N dot. Obviously 1. 1 is the identity element. Okay. Suppose I am giving you another example. Suppose Q, no. Let's take Z, no. I am taking set of natural number with addition. Okay, set of natural number with addition. What is the identity element in this groupoid? N addition. So obviously if you choose any natural number 2, okay, so you have to find out a number from the set N, so that if you add the number you will get the same result. Okay, that means 2 plus 0 you will get 2, 0 plus 2 you will get 2, or any arbitrary 5 plus 0 you will get again 5. But 0 is not a natural number. That means you are getting a point or you are getting a number, but this is not in the set N. Yes or no? 0 does not belongs to N. So you can say that 0 is not an identity element in N addition. Okay, and this is very important topic in the concept of group. Okay, so let's start today's topic. What is group? Okay, so obviously there will be a non-empty set. Okay, I am writing the definition. A non-empty set capital G is said to be, or is said to form a group with respect to a binary operation if there are total 4 conditions. Okay, if any non-empty set with the binary operation, if it satisfies the 4 conditions, then you can say that the groupoid G comma circle that will form a group. Group and groupoid both are different. Groupoid means that it is a system with the non-empty set and the binary operation, but group is totally different. Group is one type of groupoid if it satisfies the 4 conditions. Okay, there are total 4 conditions. Number one is G is closed. G means the non-empty set. G is closed under binary operation. Okay, G is closed under binary operation. So what do you mean by close? Close means, suppose G comma circle, this is your groupoid. Okay, now you have to take any arbitrary element, let's say A and B. Okay, and you have to apply the binary composition A circle B. The binary composition may be addition, maybe subtraction, maybe multiplication, anything. Okay, so you have to apply the binary composition A composition B, and now the result, let's say the result is C. If the result C, this belongs to the set G, then you can say that the set is, or G is closed under the binary composition. And if does not belongs to G, then you can say that it is not closed. Okay, for example, suppose I am taking N set of natural number with operation subtraction. Okay, set of natural number with operation subtraction. Now choose any arbitrary elements. Okay, this result must hold for all AB. All AB belongs to G. I am taking any arbitrary element. Okay, so let's say 2 and 3. Operation is subtraction. So 2 minus 3. Result is minus 1. And minus 1 does not belongs to set of natural number. That means you can say that N subtraction, this is not closed. Here the set n is not closed under the binary operation subtraction. Clear? Let's take another example. Let's Z addition. Z addition. Choose any arbitrary element. If you add any arbitrary integers, if you add any two integers, the result must be an integer. So you can say that Z addition, this is always closed under the operation addition. Okay, clear? I think the concept of closed is very clear. Okay, you have to choose arbitrary two arbitrary elements. You have to apply the operation. The result must be in the from the set G. Okay, this is the concept of close. Now next. Okay, next is number 2. The binary operation circle. The binary operation circle is associative. Associative means A composition B composition C, this is equals to A composition B composition C, and this result must hold for all A B C belongs to C. Okay, and you can find out this type of result, A composition B composition C. For example, let's take Z. I am taking Z addition. Okay, choose any arbitrary element. You have to choose 3 elements. Okay, I am taking 2 3 4. So 2 plus 3 plus 4. Okay, A composition B composition C, that means 2 plus 3 plus 4, and the result is 9. Okay, and if you calculate 2 plus 3 plus 4, again you will get the 9. That means Z addition, here addition is associative. Clear? Now number 3. Number 3 is there exist the identity element. Okay, there exists the identity element, and you know the definition of identity element. A composition E, this is equals to E composition A, this is equals to A, and this will hold for all A belongs to G. Okay, and last one, number 4. There must exist the inverse element. Okay, there exists inverse element of each element in G. And what is inverse element? Inverse element means, suppose A composition, you have to find out an arbitrary element, let's say A dash. Okay, A composition A dash, and this A dash, if you apply the operation, you will get the identity element. Okay, so A composition A dash or A dash composition A, in both cases you will get the identity element. For example, suppose Z addition, let's say I am taking the element 2. You have to find out an element. Achha, first of all tell me what is the identity or element of Z addition. Obviously 0. Now you have to find out an element. If you apply the operation addition, you will get the result 0. Which element? Obviously -2. So 2 plus the element is -2, the result will be 0. So you can say that in Z addition, -2, this is the inverse of 2. Okay, and this is called additive inverse. Okay, this is called additive inverse. Let's say I am taking another example, Z dot. That means here the operation is multiplication. So in this case, what is the identity element? Obviously 1. So if 2 is the element, any arbitrary element, so what will be the inverse element? You have to find out an element. If you apply the multiplication property, you will get the result 1. So obviously the element will be half. Yes or no? The element will be half. But is this element half? Is this an integer? Here the set is set of integer, na? But half is not an integer. That means in Z dot there does not exist inverse of each element. You are getting at least one element too whose inverse element does not exist. So you cannot say that Z dot this forms a group. Clear? If I take in place of Z, if I take, let's say the set is Q dot. Okay, now choose any arbitrary element. Let's say the element is 2. So obviously the inverse element will be half, and half is in rational number. So obviously Q dot this always have an inverse. Okay, so if any groupoid G comma circle satisfy these 4 conditions, then you can say that the groupoid forms a group. G comma circle, this forms a group. Okay, this forms a group. Now there is one more concept which is called abelian group. Abelian group. Okay, abelian group, this is also known as commutative group. Commutative group. Okay, what is abelian group? Suppose we have a groupoid G comma circle. It is saying that abelian group, that means this groupoid must be a group. Okay, with an additional condition. Suppose the G comma circle, this groupoid, this is a group and it is satisfying the condition A composition B, this is equals to B composition A for all A comma B belongs to G. That means it is symmetric. Okay, so if any group satisfy this additional condition, then you can say that this is abelian group. Okay, this is an abelian group. Now we will discuss with some example. First question. Let capital S be the set of 2 by 2 non-singular matrices. Whose elements are real numbers. Okay, S is a proper subset of M2 R. Prove that S forms a non-commutative group. Non-commutative group under matrix multiplication. Okay, so first of all, let's discuss the question. What is the meaning of this question? First of all, you are given a set S, and what is the operation? Binary operation. The binary operation is matrix multiplication. Okay, so the set is S and the operation is matrix multiplication. Now, what is the set S? Set S, this is the collection of 2 by 2 non-singular matrices. 2 by 2 non-singular matrices. That means the element of the set S, let's say I am writing S, this is equals to, this is the collection of matrices, let's say capital A. This is the collection of matrices. And what is A? A is 2 by 2 matrices. And obviously determinant of A not equals to 0. Non-singular na? 2 by 2 non-singular matrices. So determinant A not equals to 0. Whose elements are real number. So obviously the elements of the matrix A, that will be real number. Also given that S is a proper subset of M2R. M2R means set of all 2 by 2 elements whose elements are real number. Okay, S and M2R both are different. S is called, this is the subset of M2R. Okay, and what is M2R? M2R means set of all 2 by 2 matrices whose elements are real number. Okay, and what is S? S is a proper subset of M2R. In S there is additional property. What is the additional property? The additional property is here all the matrices are non-singular matrices. Okay, I am repeating again. M2R, this is the collection of 2 by 2 matrices whose elements are real number. Bas. And what is S? S is collection of 2 by 2 matrices whose elements are real numbers. Also, all the matrices are non-singular matrices. Okay. So this is your S. So S is equals to A is 2 by 2 matrices, and determinant of A is equals to not equals to 0. Also you can write that all the elements, that means A, I, J, those are from real numbers. This is given. Now question is, you have to prove that S forms a non-commutative group. Non-commutative group. So you have to show that it forms a group, and also you have to show that it is non-commutative under matrix multiplication. Okay, so let's start. So first we have to show that it is a group. Okay, and the groupoid is S dot. Dot means here dot is matrix multiplication. Okay, so let's start. Number one, we have to show that it is closed under matrix multiplication. So we have to choose any two arbitrary elements from the set S. So let A comma B belongs to S. A comma B belongs to S. That means the set A is a matrix, and this is 2 by 2 matrix, and determinant of A is not equals to 0. Yes or no? Because it is from the set S. Similarly, B is 2 by 2 matrix, and which is determinant of B is not equals to 0. So you can say that then determinant of A, this is not equals to 0, and determinant of B, this is not equals to 0. Okay, now you have to show that the matrix multiplication, if you apply the matrix multiplication, the result element will be in the set S. Okay, so let's apply matrix multiplication. So A, B, you have to show that this matrix multiplication A, B, that will be belongs to S. Okay, so actually what is the determinant of AB? What is determinant of AB? We know that determinant AB equals to det A into det B. Yes or no? And det A, this is non-zero. Det B, this is also non-zero. And multiplication of two non-zero elements, obviously non-zero. So first condition is satisfied, that determinant AB, this is non-zero. Okay. Also you have to satisfy this condition, that the determinant AB, that will be 2 by 2 matrices. A matrix is 2 by 2 matrix, B matrix is 2 by 2 matrix. So what will be the order of the AB matrix? Obviously 2 by 2 matrix. So it is satisfying both conditions. Okay. Now the third condition, if A, this is real matrix, B is real matrix, and you are applying multiplication property, obviously the element will be real matrix from the set R. That means it is satisfying all the three conditions. Okay, so obviously you can say that the result matrix AB, this is belongs to S. That means this imply S is closed under matrix multiplication. S is closed under matrix multiplication. Clear? So first condition is satisfied. Number two is associative. Actually in class 11 or 12, when you have learned the matrix, you know that matrix multiplication, this is always associative. This is obvious result. You need not to prove it. Okay, matrix multiplication, this is always associative, but matrix multiplication is not commutative. Yes or no? You have learned that AB, in general, AB is not equals to BA, but A into BA, that will be always equals to AB into A into BA now. A into BC, that will be always equals to AB into C, and this is the property of associative. Okay, so you can write matrix multiplication is always associative. Okay, is always associative. Achha, so first two conditions satisfied. Now number three is you have to find out the identity element, and the element must be from the set S. Identity, what is the identity matrix? 2 by 2 identity matrix. We know I2, na? I2 equals to 1 0 0 1. If you multiply any 2 by 2 matrix with this 1 0 0 1, you will get the same matrix. Yes or no? And obviously determinant of I2, this is 1, na? Which is not equals to 0. So you can say that I2 belongs to S. And you know I2, if you multiply with the element A or A into I2, always you will get the result A matrix. And this will satisfy for all A belongs to S. That means I2 is an identity element of S. Yes. So first property, it is closed. Second property, matrix multiplication is associative. Third property, it has an identity element. Okay, now the last one, fourth property. Fourth property is inverse element. Tell me, for any matrix, when matrix inverse exists, if the matrix is non-singular, yes or no? For every non-singular matrix, matrix inverse always exists. Here the set S is non-singular, na? All the elements in the set S that are non-singular. That means all the elements in the set S always have an inverse. Okay, so I am taking any arbitrary element. Let A belongs to S, and since A belongs to S, so obviously determinant of A not equals to 0. And if determinant of A not equals to 0, that means A inverse exists. And this is the condition, na? For every element of A, inverse must exist in the set. Okay, and now question is, A inverse exists, but is it always true that the determinant of A inverse that will be non-zero? Because the inverse element must exist in the set S. So we need to show that the determinant of the inverse element will be non-zero. Actually, it is always true. We know that determinant of A inverse, this is equals to 1 by determinant of A. And determinant of A, this is non-zero, na? So obviously 1 by determinant of A, that will be again non-zero. Okay? So you can say that A inverse belongs to S because it is satisfying the two conditions. Okay, so it is satisfying all the four conditions. So you can say that S comma dot, that means S matrix multiplication is a group. This is a group. Clear? So first part is clear. Here the question is, you have to show that non-commutative group. So I already have shown that it is a group. Okay, now you have to show that this is non-commutative. Actually we know that matrix in general, matrix multiplication is not commutative. So if the operation is not commutative, so obviously the group will be non-commutative group. So just you have to write that in general matrix multiplication is non-commutative. Okay, so hence S comma dot is a non-commutative group. Okay, let's try another example. question. Show that the set Z forms a group with respect to addition. Okay, so here the set is set of integer and the binary operation is addition. Okay, now this is not matrix addition, that's just normal addition, and set the elements are integers. Okay, this is very easy problem. Solution. First we have to show that this is the set is closed, yes or no? So let's take any arbitrary elements a comma b. Okay, so let a comma b belongs to Z. Okay, and the operation is a plus b. So if you apply the operation a plus b, so addition of two integers, so that always exists in Z. Addition of two integers always integers. Okay, that means it is satisfying the closure property. So you can show that. So Z is closed under addition. Okay, now second property, associative. Actually addition is always associative. Addition is associative on R, addition is associative on Z, addition is associative on set of rational numbers. Okay, so just write addition is always associative on Z, because this is obvious result, this is universal result, you need not to prove it. Now number three is identity element. We know that 0 belongs to Z, 0 is an integer, and if you add 0 with any arbitrary element or 0 plus a, always you will get the result a, and that will happen for every element a belongs to Z. Yes or no? So obviously you can say that therefore 0 is an identity element. Okay, so it is satisfying the three condition. Now the last one, number 4 is you have to find out inverse element. Yes or no? Let's say let a belongs to Z, set of integer, and you need to find out an element, any arbitrary element, so that if you apply the operation addition, you will get the identity element 0. Okay, and you know, if I change the sign a plus minus a, always you will get the identity element 0. That means for every element a, because a is arbitrary element na, so for every element a there exists the additive inverse minus a. Okay, and obviously minus a, this is an integer, because integer always contain the positive numbers as well as the negative numbers. Okay, so minus a, this is also an integer, minus a belongs to Z. That means you can say that inverse exists. Okay, so it is satisfying all the four conditions. So you can say that, so Z addition is a group. Okay, so what is the question? Show that the set Z forms a group with respect to addition. So Z addition is a group. Okay, now I am adding one more question. Z addition, is this Abelian group? Obviously yes, because addition on real number, that will be always commutative. So Z addition, that will be always commutative group. Okay, so in this way you can prove that a groupoid is a group or not. Okay, I am giving you some homework. You have to show that Q addition, this is group or not. R addition, this is group or not. Also you can check this is commutative or not. Okay, acha, you can find out Z dot, this is group or not. Okay, try to solve these three questions. If you have any doubt, you can ask me on my WhatsApp number 7699065115. Okay, acha, Q addition, that will be a group, R addition, again that will be a group. Okay, and but Z not, this is not a group, not group. Okay, find out the reason why Z dot is not a group. Okay, I think the concept of group is very clear. If you have any doubt, ask me on my WhatsApp number, and if you have any feedback about this lecture, please comment on my comment section. Thank you so much.